Hey there, welcome back. So in the last lesson, we talked a lot about sequences and you described a lot of different sequences, some real world and some geometric or just hypothetical. This lesson will formalize some of that vocabulary we started with last time. Let's read a little bit of information about what we're going to be doing. There are many different patterns that can generate a sequence of numbers. For example, you may have noticed that some of the sequences in the previous activity were generated by performing the same operation using a constant number. That's like when we started with 150 and subtracted 6 each time. Remember with the omelets, we had 150 eggs, we subtracted 6. Every time we made an omelet, we subtracted 6, subtract 6, subtract 6 over and over. That's one type of sequence. There were other types too, and we had different patterns. One thing to know is that regardless of the type of sequence, the next term is calculated by determining the pattern of the sequence and using the pattern on the last known term. So here's the sequences that we worked with in the last lesson. What I want you to do is pause the video and complete the table. This should take a few minutes. Let's pause the video and spend a few minutes completing the table. All you have to do is say whether it increases or decreases. I'm going to use an I for increasing and a D for decreasing. And then take a minute to describe the sequence in your own words. Pause the video and hit play when you're ready to talk about the next part of this activity. So here I've used the table to describe these patterns. And what I want you to do now is compare these sequences. Which ones are similar? What do you think? What do all the sequences have in common? Take a moment to write down what you think to number 2 and number 3. So there's a lot of right answers here. You might have said that coin collecting and positive thinking are similar because they both involve multiplication. You might have said that the ones that are decreasing are similar because they're decreasing. Whatever your reasoning is, as long as it's logical, it's correct. And what do they all have in common? Well, they can all be described mathematically. Just think about the number that they start with, and then think about the mathematical operations that occur. If you know the first number and the mathematical operations that follow, then you can generate any number of terms of those sequences. All of those sequences have that in common. Now, here's a little bit of a debate in number 4. Consider a sequence in which the first term is 64, and each term after that is calculated by dividing the previous term by 4. So like this, 64 divided by 4 is 16. 16 divided by 4 is 4, and 4 divided by 4 is 1. Now, Margaret says that the sequence ends at 1. She doesn't think it can go any further. Jasmine disagrees and says that the sequence can keep on going past 1. Who's correct? What do you think? Talk with your partner. Have a little debate. Pause the video, talk with your partner, and hit play in a couple of minutes after you've had a chance to talk about this. All right, you've hit play, which means that you're ready to talk about the dilemma that Jasmine and Margaret face. So what do you think? Does this end at 1? Well, what if I had 1 pizza and I wanted to divide it into 4 slices? Each person would get 1/4 of the pizza. What if I divided those each into 4 slices? Then I'd have 1/16. Then I'd have 1/64, and I could even keep going further if I wanted to. The short answer is that this sequence does not end at 1 because there are numbers smaller than 1, and those numbers can also be divided by 4. The sequence continues as long as you want it to continue. The domain of a sequence describes all possible terms of a sequence, and the range is describing the value of those terms. So in short, the domain of a sequence is the term numbers, and the range of a sequence is the term values. For the sequence we looked at, where we started with 64 and we divided by 4, it would go on forever and ever and ever. There's never a point in which we would need to stop dividing by 4. That means that it would be called an infinite sequence. If a sequence continues on forever, it's infinite. But some sequences terminate, and those are called finite sequences. Let's look at some examples. So, for example, consider an auditorium where the seats are arranged according to a specific pattern. There are 22 seats in the first row, 26 seats in the second row, 30 seats in the third row, and so on. Numerically, the sequence is 26, 30, 34, 38, 42, 46, 50, 54, 58, and it continues infinitely. Realistically, though, it eventually ends because the auditorium has a back. Eventually, you reach the back of the auditorium and you can't fit any more seats in there. But we could continue adding 4 forever. Therefore, even though we could add 4 forever, within the context of this problem, it does not make sense for the number of the seats to increase infinitely. The context means, now, even though we could keep adding 4, we need to stop because the auditorium would run out of space. So, let's define this a little more clearly. Suppose the auditorium can only hold 10 rows of seats. Then here's the correct problem situation right here. 22, 26, 30, 34, 38, 42, 46, 50, 54, 58. This is a finite sequence, and the reason it is finite is because this is happening in a real-world situation, an auditorium, and the auditorium is not infinitely big. It ends. And because the auditorium ends, the sequence must too. Now let's look at this. Here we have some blocks. We start out with, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We start out with 10. And then we have 1, 2, 3, 4, 5, 6. 6, 3, 1. What do you think? Could we keep on drawing these pictures forever? Talk with your partner. Remember, infinite means goes on forever. Finite means eventually it stops. So you've had a minute to talk with your partner. Let's hear from somebody. Is this a finite sequence? Does it stop? If you think it stops, raise your hand and tell us why. Now let's hear from somebody on the other side. If you think this is an infinite sequence and it would go on forever, explain why. So those were really interesting discussions you guys had. And this is a finite sequence. The reason it's a finite sequence is because I'm out of blocks. I've drawn the figure that has just one block here. And if I wanted to go further, I'd have to start having negative blocks. Let's see, we have -4, -3, -2. I guess I can draw the next figure, but it would just be a picture of nothing because my next term is 0. So I'd have 0. And then next I'd have -0. So this is a finite sequence. I'm out of blocks. I can't go any further. I guess I could say that this is a picture of my next figure, the figure that has no blocks at all. But beyond that, I can't go any further. So the next part of our lesson is a group activity. In this lesson, you've seen that many different patterns can generate a sequence of numbers. Explain why the definition of function applies to all sequences. And remember, when we talk about sequences in terms of functions, the domain is the term number. The range is the term value. So the question is, all sequences are functions. Why is that? Why are all sequences functions? Your next task is to create a sequence to fit the given criteria. Describe your sequence using figures, words, or numbers. Provide the first 4 terms of the sequence and explain how you know it is a sequence. Guys, there's a lot of pieces to this. Let's make a checklist to help. So here's the things that you have to do for this part right here. You're going to create a sequence, describe it, find the first 4 terms, and then explain how you know it is a sequence. And you're going to do that 2 times. Once for scenario A and once for scenario B. They're slightly different. The first one, this A begins with a positive number and decreases by multiplication. Part B begins with a negative rational number and increases by addition. Also, A is finite and B is infinite. You really get to master all of your vocabulary with this task. So that brings us to the end of this video. This is a group activity. You will accomplish this activity working in groups of 3 or 4. This activity should take 15 to 20 minutes, and your teacher will be checking to be sure that you're making good progress as you work.